Hello, everybody. Thanks for joining our webinar today. So the topic today is going to be GPR used in construction and how to get started. So we'll try to get through the whole workflow of what's required, what data you can collect, and how to process that data. So I can share my screen in a second. And well, others are joining, so it's 6 p.m. here in Riga, and I think we can start. It's a bit of a housekeeping to go through. So let me share my screen. So hopefully you can see my screen here. So let me introduce you to today's speakers. So Jonathan Brandley is authorized reseller and partner of SPH Engineering. We've been working with Jonathan for a few years now, so he's also us to do UK and Ireland sales, and he's also running practical demos and tests. And the second speaker today is Jan Francke. Although I have to mention he's in a remote location at the moment, so he's trying to join us, and hopefully he'll manage to join us by the time it comes to his speaking slot. So we'll keep you posted there. And then myself, I'm the head of drone-based solutions for engineering and construction here at SPH, and I've been working in the drone industry for the last decade. So today's webinar agenda, obviously there will be some housekeeping rules to go through. Intro of the drone-based ground penetrating radar. I'm going to talk you guys through how it works. And also then we're going to look at some subsurface investigations and engineering use cases. And the part 2 will consist of what's needed to get started, the equipment, what antennas, what ancillary equipment is needed to start going with the GPR on the drones. And then Jonathan's going to take the floor after me, and he's going to talk about some practical considerations and the whole customer journey, and he's going to look at one construction use case. And for data acquisition and integration into the engineering workflows, hopefully Jan will be able to talk us through there. So if you have any questions, please do feel free to use the Q&A section. Don't use the chat, as that one's temporarily locked. We'll try to answer your questions on the fly. Also, our geophysicist, Yanis Karush, is going to be monitoring the Q&A section, so he'll try to get back to you with those answers. So please feel free. And also, I have to mention the recording will be available to all who registered. So it'll be a few days, and we'll send the recording from this webinar out to you guys as well. So briefly about SPH Engineering. So SPH Engineering has been in the business for the last 10 years, and we really like to call ourselves the drone technology development experts. Initially, everything started with UGCS, which is flight planning, mission control software, where you can pre-plan your flights in complex terrain. And we've been serving industries like the mining, bathymetry, construction, entertainment, and some of the other lines of businesses are drone show technologies. As you know, GPR is part of the integrated systems. We have also integrated echo sounders and magnetometers for those safe flights, and we have some other technology that allows these low-level flights in those regards. So before we kick things off, briefly about how drone-based GPR works for those folks who don't know how GPR works. So basically it emits electromagnetic waves into the subsurface and waits for the reflection from different soil types, or reflectors as we call them, with different dielectric properties. Say you have layer of clay a layer of gravel, so those will have different dielectric properties, and that layer between the intersection will act as a reflector. And on the right-hand side, you would see a typical radargram, what you expect from the data that the drone collects using the ground-penetrating radar. I do have to mention that the GPR has been a technology around since the 70s, when the military really developed it. And actually, GPR on a drone is fairly new, and it's only been few years till this technology is made available. Here is a typical example of what the processed data would look like. So drone is flying, collecting these subsurface images, and then what you're seeing here, the parabolic reflections, is basically where the pipes are located. So first you are looking for layers, and the second one is you're looking for parabolic reflections from point like pipework and similar utilities located underground. Some of the advantages are that they can be deployed over rough terrain, where traditional GPR card is not really efficient way to collect this data. So that's exactly what we're trying to aim to do here with the drone-based solution, that's to really complement the traditional methods where simply they wouldn't be able to perform to their best ability uneven terrain, but I'll talk about the benefits in the further slides. So in terms of engineering applications, subsurface investigations in the hard-to-reach areas, some of the samples and use cases that we've seen in the past are people using drone-based GPR to non-destructively validate the completed construction works. For instance, we had a case in Middle East region where contractor built a retaining wall, and for the quality control reasons, they wanted to determine whether the actual wall was built to spec. And using our drone-based GPR, they were successfully flying these vertical tall walls and mapping out what were the actual block depths of those retaining walls, and everything came out there that everything was built according to spec. The other alternative method would have been just physically drilling holes, and that's obviously an invasive method no one wants to do once the works have been completed. Also, another use case is that brownfield sites could be full of previously buried pipework, and GPR is ideal for those. And sometimes I have to mention it takes ages to clear the vegetation for the traditional methods to be able to perform in those areas. So drone is a good alternative when you simply fly over that vegetation. But I do have to mention a slight disclaimer that obviously the higher you are from the surface, you kind of lose the penetration, and the reflection as well will be. So there will be few other things you have to keep in mind, but I'm hoping that Jan can take you through those data analysis steps. Something else that we've heard people are using the GPR for, say you have a construction project for a pipeline and you want to do the subsurface mapping, the alternative is to do boreholes along the right of way. But obviously you can't do it every single meter, so drone is a good alternative to flying and actually picking up on these. If there's any potential boulders in the way that were not mapped with the boreholes, or sudden bedrock changes, and that would mean you would have to readjust your designs for the pipe supports or similar things. Another thing that's GPR is very valuable, it's detecting voids, and obviously that affects the soil capacity. You can also determine the topsoil depth, and also the water table is detectable with the ground penetrating radar as well. And obviously, everyone's favorite, locating existing utilities within that place. So those are the typical conditions. So this slide here just gives you a brief understanding of what terrain you could possibly encounter. So you can imagine pushing a cart or driving a vehicle in these conditions wouldn't be perfect. So on the left-hand side, you can see a glacier, a snow cap being mapped at very high altitudes, and no other method could actually work. And the same goes for the right-hand side when you have swampy areas with elevation changes. Sending somebody on a cart wouldn't just be practical, but drone doesn't mind, doesn't care the altitude. So the solution that we know, you just mount the ground penetrating radar. There is some integration required. Also, radar altimeter is something that you need to be able to conduct. So ideally, you want to stay roughly 1 meter above the surface, but as you know, the elevation changes. There could be bushes in the way, so this radar altimeter would help you to maintain this level altitude flight. And simply the OEM's built-in barometric pressure sensor is not precise enough to be able to safely conduct these flights. So that was something that we have to develop ourselves to be able to conduct those flights safely. Yeah, so briefly recapping the deployment benefits of this aerial system. So steep terrain, it's not a problem, can be used on partially frozen areas, say swampy locations when they're partially frozen, wouldn't be practical with a push cart or a vehicle, deployable on unstable ground conditions, simply the PT or any other type of soil that's very hard to navigate by feet. Drone would cover that with ease. You can achieve depths up to 10 meters, but I have to say it depends on the soil conditions, dry sands, and actually dry conditions in general are favorable for GPR. And obviously the frequency that you're using, from low frequency at 50 megahertz going up to all the way 1 gigahertz antennas that we're using. So the compromise you're always having here is that with the better penetrating antennas, you lose resolution, and vice versa. With the higher resolution antennas, you lose penetration. And obviously, another great factor and benefit is that it's quiet, non-invasive. So say you have sites that are environmentally sensitive, it's a good alternative to traditional methods. Also, drone will provide you with continuous profiles when you compare it to traditional boreholes. So it's just another added bonus. And last slide, I wanted to touch on how to get started and what would be your typical considerations for those guys who are interested in starting. So obviously you would need some sort of a drone platform. We mostly work with DJI, so M300, soon to be M350 as well, are made available, and the M600s are the typical go-to platforms, but we're working closely with other manufacturers like Inspired Flight or Whisper to be able to provide alternative systems to be able to carry these payloads. Regarding the sensors themselves, so we've got a wide variety of antennas. So starting from the low frequency ones for better penetration. So we have a range from 50 to 400 megahertz, and then we can go for the higher resolution ones, starting from 500 and up to 1 gigahertz ones. Then next, what you would typically need is a flight kit. So that consists of UGCS flight planning mission software, where you can actually plan out your survey lines, and also, pardon me, so radar altimeter as well. than the sky high. So for the next, you would have your data analysis tools. We have our own GeoHammer or Prism 2 that comes in a package with those antennas that we provide from radar systems. You can also use Geolytics for cloud-based visualization. And actually any software that works with Segway formats would work for the data analysis. And in terms of last step, which is the data interpretation and the actual flying. So here at SPH, we provide in-house training. It's a tier 3 type of training, starting from basics to advanced. And you can have a full set course done within a few days to be able to progress with your GPR data analysis. And yeah, we have selected partners that can also interpret that data for you. So that kind of concludes the quick introduction. That I would like to give the floor to Jonathan, who will talk you through some use cases and the customer journey in terms of getting the kit out on the job. Jonathan, the floor is yours.
Can everybody see the screen okay? Yeah. Okay, yeah, okay. Thanks very much for that introduction. So I was, yeah, as Thomas was saying, my name is Jonathan Brindley. I run JB UAS in the UK. We are very closely working with SPH, and I'll come on to that in a bit. But yeah, this case example that I'm going to talk about today is specifically about using a particular GPR called the low frequency GPR on a drone to provide peak depth for a partner of ours in the UK, more specifically in Scotland. And they use the GPR for their surveying before they, or pre-construction, before they are looking to build roads and possibly other things as well, as part of their services that they provide. So let's move to the next screen. So yeah, as I was saying, we're kind of the sort of official reseller integrator, working very closely with the SPH engineering, talking on a daily basis. Yeah, I mean, we say UK, but we're getting inquiries from pretty much all over the world now. So I think we're kind of growing in our kind of presence. So yeah, I mean, if anybody ever wants any help, our doors are always open, and yeah, please get in touch. But like I said, we're almost we're very closely now with SPH engineering as opposed to other companies. As a business, we provide all of the systems from SPH. So you can see that one of the systems that we don't have from SPH is thermal systems, but we don't want to spend too much time on that today. We also offer the TIDLAS methane systems and GPR systems, magnetometry, and echo sounder systems. Of note on there, actually, JBUS was a major partner of the consortium that was working on the quantification solution for the University of Manchester using the Falcon methane laser. So it's kind of one of our claim to fames, and we were part of, I think it was around 6 companies that were involved in that. We're hoping that product will be out in probably somewhere in the region of 12 months' time. But that'll be a software that allows you to quantify using the Falcon laser. Also, been strongly involved, myself, been strongly involved in the introduction of magnetometry into archaeology in the UK, or sorry, drone magnetometry. and we've done a number of projects in the UK, both Roman and post-Roman eras. And more recently, yeah, we've started to get involved in this great system called the LFGPR. That particular system you can see in front of you was for Cranfield University. That's actually for soil investigations, moisture content investigations, and that's actually 1,000 megahertz, so high frequency. I'll touch on what that means in just a few seconds. So yeah, just a few bits of it worthy bits of note. So what do we provide in the UK? So we're providing all of the software, all of the hardware from SPH Engineering, and as was said earlier, we've been working with SPH for a long time now, and seeing some really good growth. We do provide support for clients in the UK, and as I said, we've done also outside of Europe as well. So let's not close the door on that. But getting involved in demonstrations, trials, and also in some cases supporting with small projects as well. From our perspective, it's all about providing the client with a sort of like a journey for themselves to become self-sufficient. So anything that we can do to help that is obviously, you know, it's something that we want to get involved in. So a little bit about ourselves. So yeah, so Metsa, I mean, Metsa worked really closely with us. They were the first client in the UK to buy the low frequency GPR from ourselves, or the drone GPR from JBUS. Metsa are a leading player in services for quality forest creation and land engineering services in Scotland. And they operate N300 RTKs with various payloads, not just GPR, but they're into optical as well. But they're providing services for the construction industry in the UK, and also helping their own business as well. So that's yeah, working really closely with Metsa. So I had said a little bit about what Metsa do. So they are building roads through peat. As we'll see in a minute, you know, they are in Scotland, but they're building roads through peats, and they need to comply with UK regulations. They need to be aware of peat depths. And they also need to understand from their own perspective that when they're going to build a road, they obviously need to know how deep the peat is, because that will have a bearing on what kind of machinery they're going to need to actually build that road. So, for instance, where they have a road that is going through very low peat, low peat depth areas, it might mean that actually they've got quite a lot of rubble and rock to get through to actually put a sturdy bridge in place, or with with perhaps utilities as well. So knowing the peat depth is really important to not only their operation, but also from a regulatory perspective as well. So it's kind of yeah, it's the ability to be able to know what those peat depths are in quite you know, arduous terrain or bad terrain is really important to them. Their current approach, as I've said here, I mean, I have been on a number of peat surveys where I've seen people literally almost disappear into peat. So they'll be walking along and suddenly there'll be a hole and they won't see it, and their leg is gone. I mean, they're in that peat, and it could end up with some serious injuries. So you know, that's kind of a dangerous thing to be doing. We don't really want that. Certainly in the construction industry, like many countries around the world, and probably in Europe as well, in the construction industry, safety is put very, very high. It's probably the highest priority. So any technology that can help them do that is a real bonus to them. And so yeah, taking that away, taking that human element away is also from them is a very good thing to be doing from a CSR perspective, never mind an operational perspective. So what does the drone GPR give them? Obviously you don't need a human going over into dangerous areas of peat for a start, but guess what? It's quicker. It can survey that area much quicker. It's able to do the same survey over and over again with very high accuracy, because we can use RTK, as you probably will be aware from the M300 RTK. You know, it has an RTK correction service capability, so we can employ that in the system. So let's just move on then to sort of what the system was, what we used. So we've already discussed in the presentation about the M300 RTK. I think many people are aware of that. That's giving this particular LFGPR around 20-minute flight time, maybe a little bit more flight time, which is you can do a lot of area in 25 minutes at the speed, even at 1 meters per second. So we're using the M300. We're using a SkyHub, and SkyHub simply is an onboard computer where we are taking the data from the LFGPR and we're fusing it with the telemetry from the M300 RTK so that we can provide a seg.y file, which is the standard format used by most processing softwares for GPR. So that's the beauty of having the SkyHub on board the system. It does all the fusing for you. It makes things really simple. And you essentially download from the SkyHub into Prism 2 software, which, as it happens, comes as a standard supply anyway, so you don't even need to go and get software. It's provided as part of your solution. And then from that, that allows us to output depths from the actual software itself. So that's the workflow, if you like. We download the data, we enter it into Prism 2, and then in Prism 2, we're able to pick out the depths and then export that data into some kind of into another system for use in GIS, etc. It was mentioned earlier about true terrain following radar. Although it is very up and down, in nature, this ground, and I'll show you an example of that in just a minute. It still means that you're able to take fairly decent control of the drone and maintain quite level flight in quite a lot of circumstances. So it's still at low level, the true terrain following radar and the algorithm that allows that to happen can accurately keep that drone at a given height so that your data is as consistent as it possibly can. And if anybody's tried to fly a drone at 1 or 2 meters, I mean, it's hair-raising stuff. So I certainly wouldn't recommend it. But the UGCS Pro mission control software, along with the true terrain following and some other bits of software as well, make it child's play, make it really easy. And that's what we all want to hear. So that brings me to the LFGPR that we used. The LFGPR is a dipole system, and you can see that from the picture. It's got different poles that will give you different wavelengths, and therefore the megahertz central frequency it will be seen as different. So for smaller poles at 300 megahertz and not shown on there, we can actually go down to 75 megahertz, and you've got poles that are even longer than what you can see there. So that's the LFGPR. As a general rule, the longer the wavelength, the more penetration you have, the higher the frequency, and I think we mentioned 1,000 megahertz before. The less you can penetrate a given material, soil material, that you tend to you see more resolution, detail, and smaller objects, basically. Certainly for looking at sediments and sedimentation, longer wavelengths are fine. There's absolutely no problem with that, because we're not actually looking for small objects. We just want to know the differences in that structure of the soil. So here's an example of the terrain that I'm talking about when we talk about Scotland. I think many of you out there will be able, you've seen this on maybe on programs or whatever, but it is very barren, and but there are lots of peat and very what we call undulating, so up and down. So you have to be very careful, and walking around on this material is really, it's not the best thing. So using a drone in this environment is ideal, because you just wouldn't want to take any other material. You wouldn't want to go over it with a handheld, and you're certainly not going to go over it with a cart. So the drone really, in a way, is the tool in the toolbox that you need. And if you've got that, then it solves a lot of problems. So yeah, that's the kind of environment that we're working with. So as I said earlier, Mets are involved in landscaping projects. They are probably one of the leaders when it comes to this in Scotland. And part of their role is building roads to join not just farms, but new buildings and new roads to other roads, and so on and so forth. So there's a lot that goes on in terms of road building. It's a big part of what they do, and they're always looking to do it in the most sustainable way, with as little impact on the surroundings as they possibly can. So the amount of data that they can get, or they're always looking for more data so that they can do that better. And I think that's what the drones are enabling them to do. They don't need to actually walk all over this this environment. They can fly over the top of it, which means you're not disturbing things that are also in the ground, which is also a good thing. So sustainability is really important to them. So as you can see in the picture, and this was actually, it was a trial, but it was a trial for a project, and it was based on a proposed route of a new road. And you can see that proposed route by the arrow, because the arrow goes from top left to bottom right, and the lines are perpendicular to that. Yeah, that's right. Yeah, so yeah, you can see that it's all in line. So as part of this project, there were boreholes taken, depth measurements taken in different positions, so that when we did the trial, the GPR, we could marry them up. We could compare them and say, did that make sense? Were we seeing what we were seeing in the boreholes and in the cores? So that's kind of setting the scene that we had this kind of check and balance in what we were seeing. So this brings me on to this profile, which we flew at 150 megahertz, which is as a standard supply is your middle pole set. So we were flying 150 megahertz at 2 meters a second, and we were seeing indications of around 2.5 meter depth penetration in the peat. So as you can see, hopefully from the profile there, and I've got to come clean here, it's actually two profiles that we fitted together, but I don't think it ruins what the messaging that we're trying to get across, which is it's clear you can see the water channel in the middle, and it's clear you can see the drone moving towards the river channel, water channel, and moving away from the water channel. And as expected, and as seen in the cores, the boreholes, it married up pretty well, actually. I mean, really quite accurately. So we were quite confident that if we were to fly that in another area to find the peat thickness where that road was going to go, we'd be quite confident that would be okay. But certainly from what you can see there, we mentioned dielectric contrast before, where you have a difference in conductivity between two materials. In this case, it's peat, and below it will be some mineral. It could be rock, rubble, and you can clearly see the dielectric contrast, the difference in conductivity, and where that difference is seen. And that difference is seen where you can see the dark lines that move down towards the bottom of the picture and then move back up and back to the top again. And that would be us moving towards the water channel and then moving away. That's showing us that where the peat and where the peat levels are, and also where the dielectric contrast is. Yeah, and like I said, we saw that in the check and balance that we did using the boreholes. So ideally, I would suggest that flying I didn't actually, wasn't present at this particular flight, but I would always recommend flying the LFGPR at probably around 1 meter a second. This was flown at a quicker speed than I would recommend, just to make sure that you get that resolution. But overall, with the RDP bit, the relative dielectric permittivity of the soil, let's just say it's called that. There's other things involved, but just say conductivity of the material, peat in this case, which is above 50 in most cases, then you would then the performance of the LFGPR in this particular case has been really pleasing. It has delivered an understanding for METSA of where those peat, where those differences in peat boundaries are, and I'm sure it's something that they are going to be able to use in the future. So that was really my last slide that I've got. Thanks for listening. I hope that just gives you a quick sort of a quick look into how the LFGPR is being used. A little bit about how easy the system comes together with the SkyHub, the True Terrain following, the UGCS Pro emission control software, and how we can all automate it as a single system. And if you do have any questions, then please put them in the chat, and by either myself or one of the others will be able to help you. But yeah, thanks very much, and I'll hand the floor back.
Thank you, Jonathan, for that explanation. Very good use case. Some interesting insights there. So thank you. Yeah, I would like to introduce our next speaker. Jan, are you there? The floor is yours.
So sorry, I'm actually filming a TV show, and we're using some drone GPRs here, so it's a little late joining in. Hopefully we can hear me. My name is Jan Francke. I don't know if Salvis has introduced me. I am a geophysicist, and I've worked solely with ground penetrating radar for 33 years now in over 100 countries. And I've been working with airborne GPR for at least 12 years. And so I'm going to be talking to you from the aspect of geophysics and radar performance. I'm not trying to sell you on anything. I have nothing to do with that at all. I am talking to you from applications and practical, where it can be used and where it can't be used. So that's where I'm coming from. I do actually make drone radars myself. I make my own radar systems for very deep penetration. So there's a vested interest in it working, but there's some challenges around it. So let's talk about this. Where can we use drone GPR? Well, in theory, we can use it everywhere, but there's some considerations around that. It's not that easy, right? So the first point, and nobody wants to hear this, but the truth is that drone GPR will always, 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 underlined, produce significantly less quality in penetration and resolution than a ground-based system. There's no question about that, and it's not about sales. I'm actually I'm telling you the truth. Why is that? Well, it's about physics, and we can't change physics. Now, the next thing to consider is that there are significant legal considerations around the use of drone GPR, particularly in the UK, in Europe, and in North America. We have specific laws that dictate that radar must be used within 1 meter of the ground surface, which turns out to actually work really well for us, because that's part of the key for this working well, is to get as close to the ground as possible. So let's talk about the physics very, very simply. Radar works off the reflection between different dielectric permittivities. What does that mean? What is this word dielectric? It actually, sorry, Jonathan, it has absolutely nothing to do with conductivity, not related factors at all. It's, when it comes down to it, it's really about moisture content. So we're going from one moisture content to another, and that could be very detailed when it comes to geology. Different rock types, different soil types in the matrix can have different moisture contents. But let's look at a worst case scenario. If I was what's called decoupled from the dielectric, which means that I am more than about 1/4 of the wavelength away from the water surface. So let's say I'm on a freshwater lake and I was flying at a significant altitude of more than, say more than 1 meter. I'm going from a dielectric of 1 for air to 81 for water. That means mathematically, I'm going to lose 80% of my signal, and there's nothing I can do about that. The only way I can get around that is if I get really, really close to the water. We're talking tens of centimeters. Now, SPH has some amazing technology that you can actually do that, right? But 10 years ago, we couldn't do that at all. So it was out of the question. So yeah, wow, we're going to lose a lot of energy right at that ground surface unless we're very, very close to the ground surface. So it's very, very important that, you know, I've seen people try to use drone GPRs from 30 meters and think they're getting data, and they're not. They're getting data from all around, because one of the other problems is something called the Fresnel zone. And what that does is it talks about the angle, the cone of illumination. When a radar antenna is on the ground, it has a certain cone of illumination. And we want that cone to be relatively narrow. We don't want data to come from all around. We want it to be as tight a flashlight as we can get. And it works when it's on the ground. It actually still works when we're very close to the ground. But if we got meters in the air, say 3, 5, 10 meters in the air, that cone widens 3 times, okay? So now we've got a massive area that we're covering. And you can imagine we're trying to get energy into the ground where we have this huge reflection and we have a large surface area. We're not focusing our beam very well, right? So that's another reason why keeping it very low to the ground is not just about trying to sell you radars or sell you drones. It's about the laws of physics. We can't get around that. So here's a real example. This is 100 megahertz in Sweden, just glacial till. The top image is us dragging it on the ground. Well, not on the ground, but within a few centimeters of the ground, say 10 centimeters off the ground, right? This is the ideal height. I'm trying to get the drone as close as possible. And this is real data. So if you can see my mouse, these are the real reflections. And if you look at the depth, you know, we're getting a good 5 meters penetration. We're going into a deeper sedimentary unit here. Now you might look at this and go, hey, what's this? This is really exciting. My God, we're getting down to 10 meters. Garbage. That's not real data. That's actually data that's coming from a reflection from a tree and a small building that's about 15 meters away. So that's not real data, but this is. Now, look what happens when we raise this antenna only 1.5 meters in the air, maybe a bit more. It was about head height. So say 1.8 meters in the air. Wow, everything disappears. I can't see any geology. What I do see are some new reflections down here. And we go, well, what the heck is that? You know what that is? That's every tree we're seeing now, and every building and every car. It's all above ground information. So to the untrained eye, if we were to look at this and go, oh my gosh, this is great. Wow, look, I got penetration past 10 meters. No, you didn't. You're picking up information from reflections that came from above ground, right? So again, I'm not selling you anything because I'm telling you, yes, go and buy a drone GPR. They work for certain applications, but you better know how to interpret the data because it's really easy to misinterpret. And wow, I see it all the time on LinkedIn of people buying these radars and going, look what we got. We got 30 meters penetration through some mine in South America. No, you did not. That's just not how physics works, right? So that's what I want to get across. So why the hell are we having this meeting? What's the whole point of this? It doesn't work. Well, wait, hold on. As Jonathan just said, there are great applications where drone GPR gives you the only data possible, or at least it's better than nothing at all, right? So yeah, we acknowledge it's not going to be as good as being on the ground, and there's some tricks around interpreting it, but there are some massive advantages. Take this project right now. We're doing a TV show. I can't tell you which it is, but it involves a swamp, and we want to map underneath the swamp. Well, I can't get a boat in there because there's reeds and stuff, and there's no way I'm walking through there with a radar. So let's put a radar on a drone and fly it as close to the vegetation as we can. And essentially, it's like Jonathan's peat bog mapping project, right? We're going to do the same thing. So there are applications. And, one of the other big advantages that actually both Salvis and Jonathan didn't talk about, not only is this about access issues, but it's also about data density. So what the industry is doing is starting to realize that the best, most useful information, it comes from high density data. Now we can do that for, let's say, utilities detection by using an array-based system, right? These are the multi-channel, 32 channels. They're very heavy, very expensive, and somewhat impractical in certain areas, except in nice wide pavements. But what's the advantage of those? If you've seen on LinkedIn some of the slices that they make, They're absolutely clear data, beautiful stuff. A child could interpret it. It doesn't take any expertise there, right? We want to get to that level. Well, we can do that with a single channel system, except I need to walk back and forth every 25 centimeters, right? Wow, that takes a really long time. And nobody wants to expose people to traffic and all sorts of other things, and it's expensive. But what if we could use, quote, our robot, so whatever type of automated vehicle, to collect that high density data for us? That becomes a game changer, right? So we can use drones to collect that high density data. And I want to give you a quick example. This is real data set from Portland, Oregon in the United States. What does real data density mean when it comes to construction industry? Because this webinar was more about construction, really. So this is a data set with I think a 350 megahertz system where the ideal spacing, sorry, Americans, I'm going to do this in metric. The ideal spacing was about 15 to 20 centimeters, right? So these guys did a survey at actually double the spacing that they needed. They did every 30 centimeters in one direction and every 50 centimeters. And that took them about 2 hours. But you know what? When we look at the slice, any idiot can see where those pipes are, right? Very, very clear. It's a little blocky, but you can draw a line and no problem at all. Let's see what happens when they start opening up the spacing. In other words, they got lazy and they didn't want to do the full proper spacing. This is the price you pay in terms of interpretability. So now it's only taken them an hour and a half, and they've saved a lot of time, but yeah, they can still see things. That's okay. But let's get it worse and worse. Let's say only 45 minutes spent on site driving this cart back and forth. Wow, I've pretty much missed an entire pipe there. I just can't see it, right? Let's get even worse. 30 minutes on site. They've only done lines in one direction, and in the Y and the X direction, they've gone every meter. Holy crap, I can't make anything out of this at all. And this is the problem with GPR, right? It works really well, but I rarely see people collecting data with a single channel system at the ideal line spacing. Wow. Well, if we could put this thing on a drone and have the drone do all the legwork, we can go back to that really clear slice information and get very, very clear results. That's what we're trying to get to with our surveys. So when it comes to data density, the rule of thumb is simply painting the wall, right? How do you paint a wall? You take a paintbrush and you go back and forth, but you don't leave spaces in between. It just so happens that the size of your antenna dictates its half a wavelength. So it dictates this spacing of ideal spacing between your lines. So yeah, if you're using one of Jonathan's very small 1000 gigahertz antennas, if you were doing a true 3D scan, wow, you'd be there all day because the antenna is very small, right? Whereas if you're using 100 megahertz, which is about 1.5 meters long, you can do much wider spaces. So yeah, for a 500 megahertz antenna, which is what we would typically use in that region for utilities detection, wow, you need a profile every 25 centimeters, every 1 foot, right? That's very hard to achieve. Nobody's going to do that by pushing a cart. But indeed, a robot or a drone can be programmed to autonomously do that. And with SPH's really amazing terrain following stuff, you know, they can do all the collision avoidance, following it up hills. You can collect some very, very clear data. So what I want you to do is, well, let me go through some of the examples of what we can do with this kind of technology. The first and most obvious one when we're talking about the construction industry, I mean, we have lots of other applications, but in the construction industry is simply pipe and cable location. It's what, 95 or 90% of GPR systems are actually used for, is finding pipes in the ground. And that's a laborious task to do unless you happen to have the space and the expense for one of these large array systems. Well, that can potentially be answered using a drone-based GPR. Now, another one we want to talk about coming up is pavement analysis. What is that? Well, it's essentially using GPR, and this has been going on for 30 years, to map different layers of pavement, both in the pavement, the asphalt, and the subgrade beneath it. And another one that hasn't been talked about a lot, but is definitely a very, very big topic in Europe and Australia, is rail bed analysis, mapping the geometry of the thickness of the ballast and the subgrade, as well as something called ballast fouling, which is the amount of contaminants within that gravel material in the ballast itself. And I'm going to talk to you a little bit coming up about mapping rebar cover in very inaccessible areas. This is not a current application, but it's literally coming within months. There's new radar systems that are coming out that will enable that, and that is game-changing for the construction industry. So, okay, great. We have some applications, and Jonathan showed a really good one there. So does the data just magically appear on my screen and I can go home and I got all my work? No, unfortunately not. As I showed you, right, it's very, very easy to misinterpret drone GPR data. Very easy to do. I see it all the time, right? And the processing of the GPR data isn't trivial. There is a few steps that if you get it wrong or you forget those steps, all your depths are going to be way off, like completely off. So they're easy steps. I'm going to show you what those are right now, but it's important that we understand the processing flow of getting that data from the drone in the SegWi format, the SEGY, putting it into some software and being able to deliver something to your client that is accurate and is actually digestible by them, right? So the first part we wanted to talk about is, well, software itself. So I'm going to be talking about software that I produce, but you know, SPH has a version called GeoHammer. There's other software in the world that processes this data. I happen to have this, so I'm going to show you. It's called Geolytics. The nice thing about Geolytics is most of the drone data sets tend to be actually rather small, unless you're doing a really large area. And guess what? Geolytics is absolutely free. It's completely free for small data sets. So if you do get yourself a drone GPR, the size of your projects, of course, dictate that, but smaller projects can be done completely free within Geolytics. So I thought I'd show you this because, yeah, it's the easiest thing that I can show you. So Geolytics is simply drag and drop your file. You download it, I guess, on an SD card or a USB key onto your computer. It's a SGY file. Drag and drop it into Geolytics. That's it, right? And Geolytics reads it all. It knows exactly where you are on the planet to a degree. Now, actually, it doesn't, because depending on which machine you get the SegWi file from, it doesn't actually know the UTM zone. You're going to have to look that up. It knows its coordinates, but it doesn't show the UTM zone. But here's an example that SPH Alexei sent me that we're going to show you, and it's just some pipes in the ground, right? This is something that would have taken me with a cart system probably, I don't know, half an hour to go back and forth and collect. I think these guys did this in like 10 minutes with a drone system, right? So here's a really good example of how advantageous the drone system is. The first step we have to do is declare to the software where the ground surface is. It is not the straight line on top. It is this one. Let me see if I can show you here. So we add a gain to it. It's called an energy decay gain, just like this. And what you'll see here, this is all being done as an animation. That surface right here is the ground surface, the one that dips away. And why does it dip away? Well, the drone is grazing up into the sky and the ground surface dips away. We want to declare where that is. And that's very important. We want to remove all that data as our first step. So how do we do that? Thankfully, there's automated algorithms that it's not AI, don't use AI, but it's, you know, it's a computer vision thing that basically tracks that straight line. So you name it ground surface, you give it a color, and you just click on it a couple times and it chases it, right? So you don't have to draw it in by hand. It does it automatically. Great, easy. That's our first step. All right, our next step is we want to take the radar data and split it into different segments. Why do we want to do that? Because quite often, if we're not mapping geology doesn't matter, it's just kind of a flat lying thing. But if we're looking for a discrete target, like a pipe, for example, it's so much easier to flip through the profiles one by one if they're all oriented the same way and they're all lined up. So in Geolytics, there's a way of automatically doing that. And what I also do is just kind of kill those extra lines that are not part of the real grid. I just press delete on those guys, get rid of them. And I have now a really nice clear grid to work on, and everything lines up in the same direction. That's a one button press. And the orientation is, you can't see it on the screen, but it's green is where it starts, red is where it's ends. Now I can just go through one by one, right? And we don't even have to interpret this. The first step we're going to do is flatten everything to that ground surface. And there's a step to do that. So what we're going to do is go into the processing. Oh, it probably wants me to press start here. We're going to go into the, select a profile, add a new process, select which horizon, done. Everything's now flattened to one horizon. Okay, we're then going to add a few little processes, and we can just do all the processing as usual. In fact, you can program this in and leave it as a default programming on your account. So the next time you get a drone data set, you plug it in, it's all done for you in 1 second, right? It's all automated. And look at this, we can see our pipes super clearly, but we need to declare the velocity. So we figure out what the velocity is on some of those pipes. The shallower ones here, I'm not sure are actually pipes, but certainly the deeper ones are more realistic velocities. We find what the velocity is, that's for the migration, and we're essentially done. We're going to do the migration routine. That'll collapse that hyperbola into a single point, so we have a nice tight target. And then we'll add our Hilbert transform. Now, if this is all confusing, don't worry about it. Geolytics is about to release in the next week or two a completely automated process where it knows it's drone GPR. It essentially does everything for you, right? So here's where we want to get to, is a point where we have some nice blobs, essentially. We'll do a background subtraction. This will all be done for you. And that's it. We've now processed our data, right? The next step is let's actually do something with it. So, let's go to the next one. So now we're going to do a slicing algorithm, and this is all automated as well. So we go into, we got to start the video here. We go into our layers and we add a new layer for slicing. Okay, and press on that and just use the magic wand tool, much like in Photoshop. It calculates all of the parameters for you that's optimal for your data set, knowing what kind of data that is. And it's going to map out all our pipes for us. And what it does is we're going to take our data and slice through it horizontally, right? So from the top down, like a cheese grater, basically, we're going to take layer by layer. So let's take a look at that right now. There's a couple pipes we can see right away, right? It's really, really simple. Our pipes stand out very clearly. And of course, the important part here is that we ensured that our profiles crossed our pipes as perpendicular as possible. So now we just need to draw in the pipes, and you don't need any expertise to do that. Geez, I think my kid could do this, right? We're just going to create a new pipe feature. So we'll call it it's a polyline in AutoCAD, give it a color, maybe give it a diameter, so it's got a bit of a 3D effect to it, and off we go. So here we go. So we're going to start at one side, and of course, if it bends, we can add a few intermediary points, but it really is just drawing in the lines. And then let's go to another level. Let's drop down to, or maybe it's slightly higher up. Yep, we'll go to the, yep, there it is. Okay, so I'll grab that one, find the top of it where it first appears, draw in another pipe. You know, I can be very precise about this, and that's it, right? I've now created my pipes. I can put this into 3D. I can take a look at this in the third dimension. I can move my slices up and down, whatever I need to do. I can bring in background maps. I can now bring in magnetometry data. I can bring in whatever other sensors I have. Actually, SPH doesn't know this, but tomorrow we should release importing of mag data as well as EM and any other geophysical information. And you've now built up a 3D model, right? And from there, it's just a matter of exporting, and off it goes to your client. So, you know, yeah, so very, very straightforward how to do that sort of thing. And modern software really enables that. So the other thing I want to show you, I realize we're just about to run out of time, is pavement analysis. Same sort of thing, right? We want to gain it. We want to draw a surface on it. We want to flatten it to the ground surface, do our typical processing, and then interpret it. That's it, and out it goes to the client. So very easy to do in modern processing software. I am going to touch very quickly on a new type of GPR that's being developed, and that's high frequency systems that have stingers that essentially can be mounted on a drone, either up or across, and that could go up and down tall concrete structures to map not only rebar depth, but also corrosion and all that sort of stuff that we do currently with rebar concrete as it is. And the last one, very, very important, is humanitarian use of drone GPR for finding buried victims within rubble. A drone can pick up, and this has been done already actually, a drone can pick up a drone GPR system and place it, shut itself down, and wait for movement. Because of course, movement in rubble comes from changes in water, right? It's all about water density and a human would change that, that signal. So it's been very successful. And as we adapt that to drones, that's going to be potentially life-saving. So conclusions, very simply, you know, drone GPR has significant limitations, but there are some advantages where access is an issue or where data density is the issue. You must be well within, you know, 1 meter of the ground surface, of course, as we talked about, and we have to be careful about how we process that data to not overinterpret it or get something that's not coming from underground. It's easy to misinterpret. But otherwise, you know, we're in a new era of GPR that's very, very exciting. Thank you so much. Hopefully nobody's fallen asleep.
No, thanks a lot, Jan, for the explanation. I found it very interesting, very insightful. Hopefully the same goes for all the attendees. We're unfortunately out of time. I think most of the questions in the Q&A section has been answered by our team, so that's taken care of. The last thing I have to mention, yeah, the recording will be available after the webinar, so feel free to share it to whoever might find it interesting. Absolutely enjoyed the talk with you both guys, Jan and Jonathan. Thanks a lot for coming on to this webinar. Looking forward to the next one. And yeah, I guess you all guys know where to find us. LinkedIn, emails, please reach out to us if there's any further questions. We'll be happy to answer them. And yeah, I enjoyed the show quite a lot, so hopefully you guys did the same way. Any final words from you guys before we close this one off?
Yeah, this is from me. I didn't realize geolytics was that good. I think I'm going to have a look at it.
All right.
Perfect. I think we can wrap this one up. So yeah, thanks again, everybody, for joining this webinar. We're looking forward to the next one.
Thanks, everybody.
Thank you so much.
Thanks.
Take care. Bye-bye.
Bye, guys. Bye. Bye.
Bye.